Sean bienvenidas y bienvenidos a la programación de Aprende en Casa, una estrategia de la Secretaría de Educación Pública para impulsar los aprendizajes.
En esta sesión nos acercaremos a las asignaturas de tecnología de tercer grado con el título ¿Qué caracteriza a un sistema tecnológico?
Como sabemos, la tecnología se encuentra presente en la mayoría de los ámbitos de la vida que nos rodea, ya sea como usuarios, creadores o innovadores.
En educación básica, la tecnología se divide en campos tecnológicos como agropecuarias y pesqueras, de alimentos, de producción, de construcción de la información y la comunicación, de la recreación y de la salud.
Es importante señalar que la asignatura de tecnología permite relacionar las matemáticas, español, geografía e historia, entre otras que contribuyen al desarrollo de saberes y su significación.
Por ejemplo, Internet es un sistema tecnológico con distintos componentes que permiten buscar, enviar y recibir información impresa, en imagen, en video o sonido, desde un dispositivo a otro.
Es lo que sucede con el uso de teléfonos celulares, pero ¿qué componentes conforman al Internet y qué características tiene?
Para reforzar los contenidos de la sesión, les recomendamos tener cerca de ustedes papel y lápiz para que anoten las ideas principales, reflexiones y actividades e incorpórenlas a su carpeta de experiencias más tarde. Cuando regresen a clases, compártanla con su docente y grupo.
Veamos el siguiente video para que identifiquen los distintos componentes del sistema de Internet y sus características.
My name is Tess Swinlock. I'm a software engineer at Google. Here's a question. How does a picture, text message, or email get sent from one place to another? It isn't magic. It's the internet, a tangible physical system that was made to move information. The internet is a lot like the postal service, but the physical stuff that gets sent is a little bit different. Instead of like boxes and envelopes, the internet ships binary information. Information is made of bits. A bit can be described as any pair of opposites, on or off, yes or no. We typically use a 1 meaning on or a 0 meaning off. Because a bit has two possible states, we call it binary code. 8 bits strung together makes 1 byte. 1,000 bytes all together is a kilobyte. 1,000 kilobytes is a megabyte. A song is typically encoded using about 3 to 4 megabytes. It doesn't matter if it's a picture, a video, or a song, everything on the internet is represented and sent around as bits. These are the atoms of information. But it's not like we're physically sending ones and zeros from one place to another, one person to another. So what is the physical stuff that actually gets sent over the wires in the airwaves? Well, let's look at a small example here of how humans can physically communicate to send a single bit of information from one place to another. So say that we could turn on a light for a 1 or off for a 0, or use beeps or similar sort of things of like Morse code. These methods work, but they're really slow, error-prone, totally dependent upon humans. What we really need is a machine. So throughout history, we've built many systems that can actually send this binary information through different types of physical mediums. Today, we physically send bits by electricity, light, and radio waves. To send a bit via electricity, imagine that you have 2 light bulbs connected by a copper wire. If one device operator turns on the electricity, then the light bulb lights up. No electricity, no light. If the operators on both ends agree that light on means 1 and light off means 0, then we have a system for sending bits of information from one person to another using electricity. But we have a problem. Let's say that, we want to send 5 zeros in a row. Well, how can you do that in such a way that either person can actually count the number of zeros? Well, the solution is to introduce a clock or a timer. The operators can agree that the sender will send 1 bit per second, and the receiver will sit down and record every single second and see what's on the line. To send 5 zeros in a row, you just turn off the light. Wait 5 seconds, the person on the other end of the line will write down all 5 seconds, say 0, 0, 0, and for ones, do the opposite, turn on the light. Obviously, we'd like to send things a little bit faster than 1 bit per second, so we need to increase our bandwidth, the maximum transmission capacity of a device. Bandwidth is measured by bit rate, which is the number of bits that we can actually send over a given period of time, usually measured in seconds. A different measure of speed is the latency, or the amount of time it takes for one bit to travel from one place to another, from the source to the requesting device. In our human analogy, 1 bit per second was pretty fast, but kind of hard for a human to keep up with. So let's say that you want to actually download a 3 megabyte song in like 3 seconds. At 8 million bits per megabyte, that means a bit rate of about 8 million bits per second. Obviously, humans can't send or receive 8 million bits per second, but a machine can do that just fine. But now there's also a question of what sort of cable to send these messages over and how far the signals can go. With an Ethernet wire, the kind that you find in your home or office or school, you see really measurable signal loss over just a few hundred feet. So if we really want this internet thing to work over the entire world, we need a different way of sending this information really long distances. I mean, like across an ocean. So what else can we use? Well, what do we know that moves a lot faster than just like electricity through a wire? Well, light. We can actually send bits as light beams from one place to another using a fiber optic cable. A fiber optic cable is a thread of glass engineered to reflect light. When you send a beam of light down the cable, light bounces up and down the length of the cable until it is received on the other end. Depending on the bounce angle, we can actually send multiple bits simultaneously, all of them traveling at the speed of light. So fiber is really, really fast. But more importantly, the signal doesn't really degrade over long distances. This is how you can go hundreds of miles without signal loss. This is why we use fiber optic cables across the ocean floors to connect one continent to another. In 2008, there was a cable that was actually cut near Alexandria, Egypt, which really interrupted the internet for most of the Middle East and India. So we take this internet thing for granted, but it's really a pretty fragile physical system. And fiber is awesome, but it's also really expensive and hard to work with. For most purposes, you're going to find copper cable. But how do we move things without wires? How do we send things wirelessly? Wireless bit-sending machines typically use a radio signal to send bits from one place to another. The machines have to actually translate the ones and zeros into radio waves of different frequencies. The receiving machines reverse the process and convert it back into binary on your computer. So wireless has made our internet mobile, but a radio signal doesn't travel all that far before it completely gets garbled. This is why you can't really pick up a Los Angeles radio station in Chicago. As great as wireless is, today it still relies on the wired internet. If you're in a coffee shop using Wi-Fi, then the bits get sent through this wireless router and then are transferred to the physical wire to travel the really long distances of the internet. The physical method for sending bits may change in the future, whether it's lasers sent between satellites or radio waves from balloons or drones, but the underlying binary representation of information and the protocols for sending that information and receiving that information have pretty much stayed the same. Everything on the internet, whether it's words, emails, images, cat videos, puppy videos, all come down to these ones and zeros being delivered by electronic pulses, light beams, radio waves, and, lots and lots of love.
Como pudimos observar, el Internet es un sistema tecnológico con componentes y características específicas.
Algunos de sus componentes son cables de cobre o de fibra óptica que se distinguen por remitir información mediante pulsos electrónicos.
Escriban en su cuaderno otro componente de Internet y un aspecto que lo caracterice.
Se puede generalizar que cualquier sistema tecnológico está constituido por componentes, como los materiales que se utilizan en el sistema, cuyos atributos lo caracterizan.
¿Qué otros ejemplos de sistemas tecnológicos recuerdan? ¿Qué componentes tienen y qué los caracteriza? Anótenlos en su cuaderno.
Veamos el siguiente video con la intención de que conozcan otras características del Internet.
Hi, my name is Paula, and I am a software engineer at Microsoft. Let's talk about how the internet works. My job relies on networks being able to talk with one another. But back in the 1970s, there was no standard method for this. It took the work of Vint Cerf and Bob Kahn to invent the Internet Working Protocol to make communication possible. This invention laid the groundwork for what we now call the Internet.
The Internet is a network of networks. It links billions of devices together all around the globe. So maybe you're connected with a laptop or a phone through Wi-Fi, but then that Wi-Fi connection connects to an internet service provider, or ISP, and that ISP connects you to billions and billions of devices around the world through hundreds of thousands of networks that are all interconnected. One thing that most people do not appreciate is that the internet is really a design philosophy and an architecture expressed in a set of protocols. A protocol is a well-known set of rules and standards that, if all parties agree to use it, will allow them to communicate without trouble. How the internet actually physically works is less important than the fact that this design philosophy has allowed the internet to adapt and absorb new communication technologies. This is because in order for a new technology to use the internet in some fashion, it just needs to know which protocols to work with. All the different devices on the internet have unique addresses. An address on the internet is just a number, similar to a phone number or a sort of street address that's unique to each computer or device at the edge of the network. This is similar to how most homes and businesses have a mailing address. You don't need to know a person to send them a letter in the mail, but you do need to know their address and how to write the address properly so the letter can be carried by the mail system to its destination. The addressing system for computers on the internet is similar, and it forms part of one of the most important protocols used in internet communication, simply called the Internet Protocol, or IP. A computer's address then is called its IP address. Visiting a website is really just your computer asking another computer for information. Your computer sends a message to the other computer's IP address, and it also sends along its origin address so the other computer knows where to send its response.
You may have seen an IP address. It's just a bunch of numbers. These numbers are organized in a hierarchy. Just like a home address has a country, a city, a street, and a house number, an IP address has many parts. Just like all digital data, each of these numbers is represented in bits. Traditional IP addresses are 32 bits long, with 8 bits for each part of the address. The earlier numbers usually identify the country and regional network of the device. Then come the subnetworks, and then finally the address of the specific device. This version of IP addressing is called IPv4. It was designed in 1973 and widely adopted in the early 80s, and provides for more than 4 billion unique addresses for devices connecting to the internet. But the internet has turned out to be much more popular than even Vince Cerf imagined. And 4 billion unique addresses won't be enough. We're now in the middle of a multi-year transition to a longer IP address format called IPv6, which uses 128 bits per address and provides over 340 undecillion unique addresses. That's more than enough for every grain of sand on Earth to have its own IP address.
Most users never see or care about internet addresses. A system called the Domain Name System, or DNS, associates names like www.example.com with the corresponding addresses. Your computer uses the DNS to look up domain names and get the associated IP address, which is used to connect your computer to the destination on the internet.
And it goes a little something like this.
Hey, hi there. I want to go to www.code.org.
Yeah, I don't know the IP address for that domain. Let me ask around. Hey, know how to get to code.org?
Y'all got it right here. It's 174.129.14.120.
Oh, okay, great, thanks. Yeah, I'm gonna write that down and save it for later in case I need it. Hey, here's that address you wanted.
Awesome, thank you.
So how do we design a system for billions of devices to find any one of billions of different websites? There is no way one DNS server can handle all the requests from all devices. The answer is that DNS servers are connected in a distributed hierarchy and are divided into zones, splitting up responsibility for the major domains, such as .org, .com, .net, etc. DNS was originally created to be an open and public communication protocol for government and educational institutions. Because of its openness, DNS is susceptible to cyber attacks. An example attack is DNS spoofing. That's when a hacker taps into a DNS server and changes it to match a domain name with the wrong IP address. This lets the attacker send people to an imposter website. If this happens to you, you are vulnerable for more problems because you are using that fake website as if it is real. The internet is huge and getting bigger every day, but the domain name system and internet protocol are designed to scale, no matter how much the internet grows.
Con el video anterior, nos dimos cuenta que Internet es una red de redes.
Y que permite la comunicación entre infinidad de dispositivos en todo el mundo. Los mensajes llegan a la dirección exacta.
Ahora bien, ¿qué características tiene Internet que permite enviar mensajes exactamente a donde ustedes lo decidan?
Reflexionen acerca de la pregunta y respondan en su cuaderno. Compartan su respuesta con su familia.
Veamos otras características del sistema de Internet. Podremos observar que la información se manda en un paquete que recorre ciertas rutas y que la llegada a su destino es fiable.
7, 6, 5, 4, 3, 2, 1.
Hi, my name is Lynn Root. I am a software engineer here at Spotify, and I'll be the first to admit that I often take for granted the reliability of the internet. The sheer amount of information zooming around the internet is astonishing. But how is it possible for every piece of data to be delivered to you reliably? Say you want to play a song from Spotify. It seems like your computer connects directly to Spotify's servers, and Spotify sends you a song on a direct, dedicated line. But actually, that's not how the internet works. If the internet were made of direct, dedicated connections, it would be impossible to keep things working as millions of users join, especially since there is no guarantee that every wire and computer is working all the time. Instead, data travels on the internet in a much less direct fashion.
Many, many years ago, in the early 1970s, my partner Bob Kahn and I began working on the design of what we now call the internet. Bob and I had the responsibility and the opportunity to design the internet's protocols and its architecture. So we persisted in participating in the internet's growth and evolution for all of this time up to and including the present. The way information gets transferred from one computer to another is pretty interesting. It need not follow a fixed path. In fact, your path may change in the midst of a computer-to-computer conversation. Information on the internet goes from one computer to another in what we call a packet of information. And a packet travels from one place to another on the internet a lot like how you might get from one place to another in a car. Depending on traffic congestion or road conditions, you might choose or be forced to take a different route to get to the same place each time you travel. And just as you can transport all sorts of stuff inside a car, many kinds of digital information can be sent with IP packets, but there are some limits. What if, for example, you need to move a space shuttle from where it was built to where it will be launched? The shuttle won't fit in one truck, so it needs to be broken down into pieces, transported using a fleet of trucks. They could all take different routes and might get to the destination at different times, but once all the pieces are there, you can reassemble the pieces into the complete shuttle and it'll be ready for launch. On the internet, the details work similarly. If you have a very large image that you want to send to a friend or upload to a website, that image might be made up of tens of millions of bits or ones and zeros, too many to send along in one packet. Since it's data on a computer, the computer sending the image can quickly break it into hundreds or even thousands of smaller parts called packets. Unlike cars or trucks, these packets don't have drivers and they don't choose their route. Each packet has the internet address of where it came from and where it's going. Special computers on the internet called routers act like traffic managers to keep the packets moving through the networks smoothly. If one route is congested, individual packets may travel different routes through the internet, and they may arrive at the destination at slightly different times or even out of order.
So let's talk about how this works. As part of the Internet Protocol, every router keeps track of multiple paths for sending packets, and it chooses the cheapest available path for each piece of data based on destination IP address for the packet. Cheapest in this case doesn't mean cost, but time and non-technical factors such as politics and relationships between companies. Often the best route for data to travel isn't necessarily the most direct. Having options for paths makes the network fault tolerant, which means the network can keep sending packets even if something goes horribly wrong. This is the basis for a key principle of the internet, reliability. Now, what if you want to request some data and not everything is delivered? Say you want to listen to a song. How can you be 100% sure all the data will be delivered so the song plays perfectly? Introducing your new best friend TCP, Transmission Control Protocol. TCP manages the sending and receiving of all your data as packets. Think of it like a guaranteed mail service. When you request a song on your device, Spotify sends a song broken up into many packets. When your packets arrive, TCP does a full inventory and sends back acknowledgments of each packet received. If all packets are there, TCP signs for your delivery and you're done. If TCP finds some packets are missing, it won't sign. Otherwise, your song wouldn't sound as good, or portions of the song could be missing. For each missing or incomplete packet, Spotify will resend them. Once TCP verifies the delivery of many packets for that one song request, your song will start to play. What's great about the TCP and router systems is they're scalable. They can work with 8 devices or 8 billion devices. In fact, because of these principles of fault tolerance and redundancy, the more routers we add, the more reliable the internet becomes. What's also great is we can grow and scale the internet without interrupting service for anybody using it.
The internet is made of hundreds of thousands of networks and billions of computers and devices connected physically. These different systems that make up the internet connect to each other, communicate with each other, and work together because of agreed upon standards for how data is sent around on the internet. Computing devices, or routers along the internet, help all the packets make their way to the destination where they're reassembled if necessary in order. This happens billions of times a day, whether you and others are sending an email, visiting a web page, doing a video chat, using a mobile app, or when sensors or devices on the internet talk to each other.
Nos hemos dado cuenta de que Internet es un sistema tecnológico con diversos componentes y características que permiten comunicarnos con muchas personas en todo el mundo.
Ejemplo de esto son las redes sociales que posibilitan conversar de asuntos cotidianos, aspectos laborales o académicos.
Con sus propias palabras, respondan en su cuaderno la pregunta: ¿qué caracteriza a un sistema tecnológico?
Además, elaboren un pequeño texto acerca de una característica o componente de algún sistema tecnológico,
como el sistema de transporte público, del sistema de paquetería o del sistema hidráulico.
Estos u otros sistemas permiten que el transporte los lleve exactamente a donde quieren llegar, que envíen un paquete a otra ciudad, que el agua llegue a su casa o escuela. En fin, pueden surgir otros ejemplos.
Elaboren un dibujo, croquis o maqueta del ejemplo seleccionado. Recuerden incorporar sus actividades en la carpeta de experiencias y compartirla con sus compañeros y docente.
Les recomendamos la lectura del libro Bio. ¿Qué? Biotecnología, el futuro llegó hace rato, de Alberto Díaz, que explica las relaciones entre la ingeniería y la biología. Incluso podrán identificar otros sistemas tecnológicos.
Fue un gusto compartir esta sesión con ustedes. Los esperamos en una más de Aprende en Casa.
¡Hasta la próxima!